Hello, welcome back to the Honors Pre-Calculus video tutorial series for Chapter 10 on Statistics. Today we'll go into Part 1 of Section 5, Statistical Literacy. So, the topics we're going to cover today are the uses and misuses of statistics, correlation, and the importance of randomness. Way back in section 1.7 at the beginning of the year, we mentioned R, the correlation coefficient, along with capital R squared, the coefficient of determination. We suggested using the closeness of R squared to 1 as a measure of how well a curve fits the points of a scatter plot. Later on, we noted that statisticians commonly use little r for a similar purpose, but always measure as how close the data points are to a straight line. We now want to be a little more emphatic about that point. Figure 10.27 shows what we call a positive association between the y variable and x variable. Listen to the terms, positive association. Generally, as x gets larger, y gets larger. So, because the underlying relationship appears to be linear, it's appropriate to consider the correlation coefficient. Because the line slope is positive and is close to +1, because the line's points, or the points are close to the line, it's appropriate to say that there is a strong positive correlation. So again, we use the word correlation when the data appears to be close to a linear model. Otherwise, if there is an obvious pattern between the x's and the y's, we just say there's an association between the variables. Now, if we look at figure 10.28, well, definitely we see that as x increases, for the most part, with a few counterexamples, y appears to decrease. There is a line with a negative slope that appears to fit through it. So you'll notice under each of these we'll see what the correlation coefficients are. For the first one is 0.975, which is quite close to 1, very strong positive correlation. And in the second one it's negative 0.689, which is a little weaker, a little farther from -1, but definitely negative. So we would say that figure 10.28 demonstrates a weak negative correlation. Remember, don't use the word correlation unless the underlying data connection is a linear model. Now take a quick look at figures 10.29 and 10.30. There's a definite pattern to 10.29. In fact, most of you would instantly recognize that as apparently quadratic, definitely not linear. However, it is an association, not a correlation. In fact, the data to the left of the vertex would appear to have a negative correlation, and the data to the right of the vertex would appear to have a positive correlation. So we don't even talk about correlation in this case. In the next example, there's very, very weak relationship. It's hard to even imagine, is there a line that fits through the data? It does seem like we start high to the left and wind up low to the right. So it is kind of conceivable that there is some sort of a negative correlation. And in fact, you see that the correlation coefficient is negative 0.227, but that is a very weak negative correlation. So let's go over the rules for using correlation correctly. So, correlation correctness. First of all, the variables need to be quantitative, not categorical. So you couldn't plot red, blue, green against happy, sad, because those are categorical variables. They have to be numerical variables for both x and y. If no scatter plot's shown, ask yourself, could you make one? Make sure that the underlying pattern in the scatter plot is linear. Strength of correlation is not an appropriate measure for data exhibiting nonlinear behavior, like in the quadratic example we just saw. Also, don't confuse association with correlation. Association is a much broader term. You can even apply it to categorical data. whereas correlation should only be used for quantitative data to measure the strength of an association we believe to be linear, no other mathematical model. Also, correlation doesn't imply causation. Even if the points line up nicely, it's tempting to conclude that the variable y is reacting to the variable x. It might be the other way, or the two variables might be each reacting to a third variable. So correlation does not imply causation. So let's test your understanding of this concept. In each of the following cases, let's decide whether the word correlation is being used correctly. And let's point out any statistical errors. First, a graph of per capita gross domestic product Y against literacy rate X for 17 world countries is shown in figure 10.31. Listen to this statement. The strong positive association with R equals 0.788 proves that raising a country's literacy rate will improve its per capita gross domestic product. Well, first, it's good that they use the term strong positive association rather than correlation. It may be inappropriate here to report the correlation coefficient R, since it might not be linear. In fact, if you look at what's going on at the end of the data, there could be some quadratic or exponential curve. The biggest error, however, is jumping to the conclusion that because there's an association between two things, there's a causality. Remember, they could both be due to a third thing. Increasing the literacy rate could have no effect at all on the per capita gross domestic product. Number two, a research company reported a strong correlation between religious affiliation of American adults and the types of charitable organizations they support. Well, right off the bat, this is wrong because religious affiliation and types of charitable organizations supported are categories. They're not quantitative. You cannot talk about a correlation between categorical, only quantitative variables. Number three, a famous study of college freshmen once showed that the high school measure that had the highest positive correlation with freshman GPA in college was the number of mathematics courses taken in high school. It showed that the best preparation for college was to take a lot of math courses. Again, they're assuming there's a connection between correlation, if it exists, or a strong association, implies causality. It does not. It could be that both the GPA in freshman year and the number of high school math courses are both responding to some third variable, like the academic motivation of the student. So just increasing the math courses, if you don't increase motivation, would have no effect. The last one's kind of funny. In 1990, a researcher measured the heights and annual salaries of all people named Michael Jordan in the city of Chicago and had an astounding correlation of 0.97, which suggested a strong linear relationship between height and salary among the group. Everything here is actually correct, except that the researcher shouldn't have been astounded. One of the Michaels had an unusually high salary and an unusually high height, causing the scatter plot to look something like this. The only reason that a linear model fits it so well is because of one very unusual point, which really results in a misreading value of R and a misleading regression equation. Beware of extreme points when analyzing correlation. We also said we were going to talk about the importance of randomness today. As we mentioned earlier in the chapter, the aim of statistics is to draw meaning from data. The real goal extends beyond the data. Inferential statistics uses collected observations to draw conclusions about broader populations and real-world phenomena. Statistical inference absolutely depends on randomness, ironically, because it's so predictable. Let's take another look back at the example 11 from 10.3. You probably remember it. It inferred a fact about loon chicks in the population. The inference was based on a sample of 30 loon chicks. It was vital that we trusted these 30 loon chicks as being typical of the overall population. What if we had taken all 30 chicks from a single wildlife preserve? Would that have made a good data set? Probably not. Suppose a later study were to show that that particular preserve produced unusually large loon chicks. That would render our data useless for making inferences about the population of all loon chicks. So it's very important that we randomly collect data. So let's take a look at some examples and think how random they are. So which of the following sampling strategies would result in random samples from the population under consideration? Number 1, your school wants to pick 5 random seniors to represent the school on a district panel. The names of the seniors are written on slips of paper and placed in a bucket. After the class president shakes the bucket, the blindfolded principal draws 5 names. Unfortunately, this strategy rarely proves to be random since the names usually enter the bucket in a non-random order, for example alphabetically, and the typical shaking doesn't really compensate for that. As a result, the names that were entered last, perhaps close to the end of the alphabet, are always going to be closer to the top and have a better chance of being chosen. Apparently, this phenomenon famously affected the 1969 Selective Service Draft Lottery. Number 2, a group studying the increasing problem of obesity in America wants to estimate the percentage of American teenagers who order hash browns with their breakfast sandwiches at a particular national fast food chain. They visit each of the chain's restaurants in Ohio and gather data from the first 10 teenagers they see ordering breakfast sandwiches in each restaurant. Is that a good example of randomness? No, it is not. Idaho has no guarantee of being typical for the purposes of this study. For example, Idaho is a famous potato growing state. Maybe people are more partial to potatoes in Idaho. Secondly, if you grab the first 10 teenagers, that's not random. It might be groups of friends arriving together that are like-minded, or even they might be, if they grab the first 10, they might be the hungriest and therefore most likely to want potatoes. Who knows, but it's definitely not a random strategy. And finally, number 3, the Miss America contest wants to choose 8 state representatives at random for a publicity shoot. Each of the 52 women is given a card from a well-shuffled deck. The publicity chair then chooses 8 cards at random from another well-shuffled deck, and the women with the matching cards go to the shoot. Is that random? Yes, this one really is random. Notice that this method is quite carefully designed, but that's not what really usually necessary for attaining randomness. We will return to this point at the end of this section. Anyway, that's enough to get you started on the homework, which is pretty intuitive, and I'll get the second video lecture out as soon as I can. Thanks and stay well, and hope to see you before too long.